Okay, welcome to the last of the Python tutorials for NITARP. I'm think mostly speaking to people who are going to be watching it later. Thank you, the brave souls who will join today. Okay, so we left off up to the point where we could do programming, create functions, have some idea of how to control the flow of the program, and get from point A to point B. We're going to finish off here with some graphics capabilities and some extra topics that don't fit anywhere else. So I'm going to start. Oops, it doesn't seem to work. Give me 1 second. Okay, so I think I'm going to primarily just stay outside of the presentation mode. That's unfortunate. Let me see if I can do better with the PDF version. Okay, so that's better. Let's move along here. The topics to be covered today, just touching again on libraries and talking about some basic concepts about the programs, and finally plotting. We don't get to anything fancy. You get your feet wet and your appetite wet for what Python is capable of as far as plotting goes. Okay, so first of all, libraries. I introduced the concept last time, and the idea is that once you write a set of functions, essentially that gives you your programming, your library. And that library you can then exploit. You don't have to duplicate the same functionality that you need when you need it again. And you can share whatever code you write in the form of a library with your collaborators. And it's essentially there to add functionality to Python and then allow others to use the same functionality. So it's a bit more efficient all around, especially in a big collaborative effort. And the key to understanding and using the libraries is something called the programming interface. API, which I may come back to over and over. That's a fairly generic term. It mainly in programming, it mainly deals with how you're going to be able to call the various low-level functions within a given library. So that includes what arguments are expected, what name to call that, and what arguments or parameters may be additional optional values for you to try within the function. Okay. So before I go further, NumPy is an example of a Python extension, which is a library. It extends the numerical capabilities. Okay, so what do I mean by API? So last time in session 4, we talked a little bit about defining a function, and this is the example that I've lifted from the slides from last week. So I defined my math tool. I guess that you have to ignore the little red lines that are telling me that this is spelled incorrectly, but that's okay. Python knows that it's fine. And the API is everything that's in the bracket and what I call it. So when I want to use it, I would say my math tool. That's how I would call it. That's how I defined it here. It's expecting A and B, or values for A and B. It's not expecting the actual A and B. And if you want to change the default operation, then you have to select one of the allowable operations here. API will tell you all of that. It'll tell you the name. It will tell you the parameters that are expected and what values are allowed, or at least a well-written API in Python. So when you're learning a library such as NumPy, what you're really after is finding this API first and foremost. On top of that, the help file can tell you exactly what's going on, if it's a complicated algorithm that's in place, or if it's a function that does plotting, why was it written, who wrote it, what was the purpose, and what exactly is it going to do to the data that you're going to pass on to it. But the very basic minimum is the API. Okay, so again, you just need to learn what the API is, and you get a handle on what the library is. And libraries or people, collaborations, that includes you, who write these libraries, it's always good practice and always recommended that you adapt naming conventions, that you adapt a certain style that people, after a while, people can start guessing at what the parameter names are going to be called or what the function names are going to be called. You also want to tie it into the functionality itself, so to make the guessing a little bit easier, or if not the guessing, the searching a little bit easier. NumPy has a median function, and so obviously it calls it median to make it easy for us to do, and it is expecting a set of values in a NumPy data array, and that is consistent amongst all of the various NumPy statistical functions. So they are mean, median, standard deviation, whatever have you. They're all expecting the same thing. Okay, so the same should go for you. Who just joined?
Margarita.
Okay, well, welcome.
Thank you very much.
Sure. Okay, we're continuing on with libraries here. So the key thing that you might be asking at this point is, how do I find the API and the description? And usually there's online documentation, particularly for the major packages such as NumPy. And here, for example, we come back to the idea of NumPy median. If you follow one of the many links that are in the various presentations by now to NumPy, you can look for the documentation, and either it's identified as an API or programmer's interface, and it should, and a well-written one should at the very minimum include all of these things that you see here. So median, that's the name of it, then a set of arguments, and again the optional ones have the equal to sign, mandatory ones have no equal to sign. A short description, compute the median along the specified axis. Return the median of the array elements. So here we have A, which is the input, the numbers for which you want to know the median value. Axis is optional, and when you are trying to compute the median of, say, multi-dimensional arrays, you may not want to have the median of every single thing, but you might want the median of all the rows, or you might want the median of all the columns, or you might want the median for a particular pixel in the time or the z direction, the third dimension, the readout. And the rest of it's defined here, and obviously very key, what does it return? It returns the median value. Okay, this is what you should always look for in the library, and this is what you should always prepare for yourself if you want to share your code. Okay, that's pretty much it on API. We're going to touch on a couple of new programming topics, that is objects and methods. So far, when we started this, we talked more about variables, accessing files, storing files on the disks. Okay, in programming, in there are objects that are a bit more fundamental constructs, and they could be many different things that ultimately you can use, call on, manipulate, and examples of that are variables, but also containers, complicated data containers that are built on a series of variables any number of those could be objects. Okay, a strict definition of an object would be that you define what's called a class in Python. Okay, at this level, we're not concerned with that, but you should know that there are such things as objects. And the reason you should know that, and you should always think of variables as object, because each object has associated with it a certain methods or functions. Okay. And these methods and function allow you to manipulate or pull information about the object or whatever it contains, the data that it contains within that. Again, this is some of the more core fundamental concepts in programming. We're only barely going to touch that here. I'm just going to introduce them, but they're extremely useful. And as you progress further in programming, you'll get to learn how to access these methods and learn how to look for them for each of these objects. So here's your first foray into it. So define an object. In this case, we're going to use the np0s object, and we call on the np0s function. We supply it a couple of arguments. Primarily, we want it to be of the length 10. And after that, we want it to be type integer. So we define that. The zeros API for NumPy will tell us that this is how you're going to call it. The end result is this array, integer array in this case, length 10. It's stored in the variable z. Well, actually, it's stored somewhere in the computer. Z is just your handle to this part of the memory where you can then play with it. And z is an object. Okay, it's a NumPy zeros object. It was created by a class that's defined by NumPy zeros function. Okay, NumPy itself is also an object, but we're getting ahead of ourselves here. Now, z, okay, that's our handle, has a lot of methods that come for free. Because it's an object, and for this object, the programmers define those. If you were to issue the command dir in parentheses z, so it's a bit like directory or directions, however you want to remember it, but it's dir, and then give it the object. Everything that's in quotes here, all of these, every single one of them is a method. A method is a function that you can call on to manipulate, to provide further manipulations or gather information. Okay, we'll come to that in just a bit. But first of all, notice that there are some that look more or less like words and functions that we're used to. And then there's plenty here, nearly half of them, that begin with 2 underscore and end with 2 underscores. For the most part, you should ignore everything that starts with 2 underscores and ends with 2 underscores. We're not going to get into details here as to why these are special. This is a naming convention adopted by Python developers for certain special functions or methods. Okay, so ignore that. The rest of these are here, and some of these you can pretty much guess as to what they will do. If you access the min method here, you will get, say, for example, the minimum value. Okay, z.max gets you the maximum value. Okay, that's how you call up these methods. You take the object, add a dot, and then the name of the function or the method. So z dot any of these will allow you access to that function. Some of them will require you to put into parentheses. Some of them you don't have to put in the parentheses. Some of them you are required to put the parentheses and provide arguments. And like z.max, there are some where you just call and you don't need to give it any arguments. Okay. If you were to type in z.max, you will get the maximum value, which would be 0 because we created this using np.zeros. You wanted to find more help on z.max, you simply type in help. z.max and open close parentheses. Same goes for any of these. If you're curious about what transpose does, if you're curious about what trace does, if you're curious about what sort does, copy, obviously, choose, byte swap, arc sort, don't necessarily need all of them. But if you want to know more about it, that's what you would do. You can that would be one way. Or you would go and look up API for Z. Okay. Another sort of a miscellaneous leftover programming concept is that sometimes when you're writing a line of code, you might find that there's just far too many arguments, or you've just been really super descriptive about how things are, or there's just too many parameters that you needed to pass to it, and it just, if you were to keep writing it, it will just create a 256 character or 400 character line, which is not very pleasant to read by horizontal scrolling or otherwise. So you want the capability to break the line so that the same command could be split over multiple lines. And Python allows you that. It allows you that through this construct here. Here I'm defining a very long array that I call call names. And these call names are it's nothing more than a primitive Python array. But it has a lot of different values. Okay, they're all defined here in strings. And if I were to write them all out, it would be an incredibly long line. So instead, I'm putting the backslash here. Okay, and when Python comes to this backslash, it in effect grabs it and sticks it at the end of the line here. Same here. It will keep sticking it, so it thinks of it as a single line. But to you, the programmer, the human, it's a lot more easier to look at this and understand what you did. You can also group things. So one of the reasons I say you should think about it is you can group items that are similar so that they're easier for you to access and manipulate. So here, for example, things having to do with IRAC are in this line. W happens to be Ys. So things that have to do with Ys are in this line, and so on and so forth. Okay. That's the idea with the line continuation. Okay. Now, one last command that I should tell you about is exec file. You can put that inside a script and then give it a name of another Python script. An exec file would happily go and execute all of those lines for you. Very useful. You can write one script to do a set of instructions. Then you can call that script this way. Okay. In reality, Python doesn't really prefer that. What you should do is define a library, call the library like you would NumPy. You don't want to be calling exec files for all of the functions that are in NumPy. But developing those kind of libraries is beyond the scope of these set of tutorials, so I haven't discussed them here. But the exec file is a nice, easy way, at least to execute separate the code into a bunch of files and then interconnect their execution. Okay, so that was a series of leftover concepts that should help you with your programming. So any questions?
No, thank you very much.
Okay. All right, the last topic we're going to cover is actually going to be a demo, and that's going to be two-dimensional plotting. It turns out that just like NumPy has been very useful at extending numerical capabilities, and SciPy has been very good at extending scientific capabilities, and AstroPy, which we haven't really talked about too much, is very good at extending astronomical utilities for Python. There are a ton of extensions that have to do with plotting. Simple 2D plotting, image plotting, any number of those. And if you were to go and start taking a stock of this, for example, at this particular wiki page, you're going to find that you're overwhelmed. So here's a recommendation: stick with matplotlib. It's based on another popular scientific package called MATLAB, and matplotlib and some other variations of it are probably the most powerful and somewhat easy, but not necessarily super easy capabilities for plotting. Okay. All right, so we're going to step out of the presentation mode here. And we're going to call up Spider. So here it is. This is now going to show you some of these things that are best shown. So on the tutorial website, let's go there very quickly. For session 5, you will find the tutorial slides, but then the demo that we're about to go through is right here. Okay. And lastly, I've found a cheat sheet which you may find useful as a quick reference. If you just look at it now, it's just kind of a dump of everything. But once you start getting used to the plotting and you just are trying to remind yourself, what is it called? These kind of cheat sheets could be useful for that. Okay, so I'll leave it at that. Let's go back to our Spider session. And in the Spider session, which by now you should be familiar with, you're going to start up with your series of commands and other things. And here what I've done is strung together a few examples of plotting. Okay, we're going to begin with example 1, which is a very simple plot. Okay, now this is something we're going to do live. We're going to use the data from ipacktabledemo.py. Okay, this is from last week, where you looked at some WISE data. Let me show you. At the end of session 4, there was the WISE Owl Sky data, and there was a demo for reading the data into your Python session. And that's what this looks like. Now what we're going to do is we're going to simply execute that, and at the end of this, if you recall, everything was in the variable called wdat. Okay, and we're going to take plotting over from wdat. So before we begin, one easy way we can do that is I can say exec file and then the name of my program, which is ipacktabledemo.py. Okay, easy enough.
Yeah, sure.
Except, yeah, I may need to tell it where this thing is. So, since I haven't set a current working directory, I will just go ahead and put in the full path name that I just cut and pasted. So now my line 12 says that. And if I were to execute it, it happily goes about. Look at this. Oh no, what do we got? Oh, of course, I have to set my current working directory. Otherwise, this one wouldn't know. Or I have to change my table demo. So, okay, so now that was just a simple matter of making sure that the data are read. And if you recall, this thing goes through and then prints a whole bunch of values out. And so it's done that. It's gone through and given us all of this. Now, this should have the variable wdat. So let's try this. And here we go. In the bottom right-hand corner, you can see that we have the variable wdat. It has all of these columns that we read in from the IPAC table that I downloaded from URSA. So now we're set to go. The first thing that you do before you get to use the programming, the plotting library, obviously is to import it into your session so you can use it. So here's my import statement, and I'm going to now read them all in as PL. So everything that's included in this library gets PL dot. Okay, PL is my handle into the library. A reminder again that I want to do this because I don't want any conflicts with any other library that might also have some of the same command names as the plotting library. No chance of that, but this is good. The very simplest thing that you can do is to plot y versus x. Okay, and here I've chosen to plot declination versus right ascension. Okay, just to show you where the locations of the objects are in this catalog. A simple y versus x takes actually 3 lines in Python with MATLAB. With other libraries and with other certain constructs, you don't have to. You can just issue the plotting command itself. But in this case, that's sort of the very basic minimum that you can do. You start by defining a new figure. You say figure, open close parentheses. Okay. Again, you're calling a function here. An open close parentheses means it doesn't have any mandatory parameters, but of course it has a ton of parameters that you can specify in it. The API will tell you. For example, you can specify the size of the plotting window or the size of the saved figure that you might put into a file, like a PNG file or a PDF or an EPS or a PostScript file. But that we're going to ignore that and go straight into our plot. So to plot it, it's pretty simple. It's plot. Okay, access it with pl dot. Give it an x, give it a y, and then finally it happily takes that command. It happily takes the figure command. It starts a figure. It does its plotting, but it still wouldn't show you the result until you say, okay, show me. All right. So let's issue these commands and you can see what happens. Okay, what happened was that the plotting command where's the plot? Let's try it again. There it is. Okay, for some reason it didn't show the first time around. So I've moved it over a window. I'll bring it over here. This looks like a jumbled mess. A bunch of numbers that, because we know we issued the RA command of the X, they should be RA in degrees, some number which is declination in degrees, and then a bunch of commands. So what happened here exactly? Well, what happened was that plot says, show me y versus x, and connect all the data points. So x versus, or y versus x connected on RA and DAC is just a mess. So we don't want that necessarily. But we do if we're doing, say, where it does make sense to connect the dots. So let's go to example 2. Example 2 is very similar, except now, okay, let me find the result from example 2. Looks like we have to issue everything twice for some reason. All right, give me a sec. Why is this not? Okay, my mistake. For some reason I didn't issue this, and for some reason it didn't appear. But here it is. So what I asked for in the WISE catalog was give me all of the known detected WISE sources centered around M42, which is in Orion, out to a radius of, I forget, 10 or 20 arc minutes. What you're seeing is location of stars with a central area blocked out, except for a couple of sources. This central area is basically saturated in white, so there's no stars there. And the outer circle is the edge of my search limit. So that's essentially what I asked for, and that's where they are. The stars and this makes a little bit more sense than connecting these dots. We actually want the position. Okay. But again, you've seen two ways to do the plotting here. One is to connect using plot. So this is a continuous line. The other one is to plot individual plots, which is a scatter command. Okay. But let's move on here because we've done something very basic, but we probably want something a little bit more. So let's see what else we can add to sort of control the flavor and look and feel of this. We can issue the scatter command, but this time there's a whole bunch of colors that we can also change. A whole lot of other options, and one of the ones we're going to use is red. So let's try that. And then we're going to put in labels, and we're going to put in labels on x-axis, y-axis. Then we're going to just simply put in a label that we call text label just on the plot itself. Then we can save it and we can close it, but we're not going to do that. So I'm going to run up to this command here. Okay, and again, this command figure issue starts a new figure. Then we issue a scatter command, then we issue a label command, then we issue a label command, then we issue another label command at this location that just says that. But we haven't issued pl.show. So let's do that so you can see what it is, and then we can save it. Of course, it has a habit of... Sorry, I have to do everything twice for some reason in this session. But here we go. Now everything appears again. It's in red. I noticed that my RA is now called RA, and my declination is now called declination. And on top of that, the points are in red. Okay. Now you can do a couple of additional things here. You can save it as a file. We'll call it example3.png. And then you can issue a final thing called close, and that closed that whole figure so that it would save it to your... Sorry, I don't mean to give you to spin your head too much here, but I need to close some of these things manually as well. But then this thing is gone, so next time you issue a plotting command, it has nowhere to go, so you'll have to start again with figure. Okay. So far you've done simple scattering, scatter plots, and connected line plots. We've used it to plot right ascension and declination. I'm going to continue that with one more example, and that is to show you other capabilities that are present in the plotting library. You can also get a histogram using something called Babar. So let's see what that looks like. Okay, so today is the day everything has to be issued twice. I apologize, I think it's something in my environment that's doing that. Okay, spinning wheel. Okay, I'm not sure where it went. Oh, I see, there's an error here, but now the error is gone. There's more error. We may be experiencing some differences in the API here. Is this okay now? Okay, I still don't have it. I apologize. This did work when I tried it. Okay, so we'll skip this. I'll come back to it and see if I can rescue it. Let's move on to some of the other capabilities. And in particular, one of the most common uses of plotting is a color magnitude plot. And so this is one way we could do that. The WDAT array, so let's take a look at the bottom right part. Call names. Okay, there we go. Something is a little bit screwy here. That contains not just the RA and DAC, but it contains also a lot of photometry. The WISE photometry has names like W1M Pro, W1 Sigma Pro, signal to noise, where W1, W2, W3, W4 are the WISE photometer bands. It also has some 2 mass data, so JH and K data are also here. That's within some sort of an automatic cross identification, which may or may not be reliable, but that's up to your science. So what we're going to do is to take the W1 magnitude, which is the column name is W1M Pro, and then we're going to subtract from it the W2 magnitude, and so we get W1 minus W2. And then we add to that, and then that's our x-axis, and the y-axis is going to be our W1 M Pro itself. So this is a color magnitude diagram. And again, 3 simple plots, and then we're going to make it a little bit better. Okay, so we're having some problems with that, my spider setup. So I'm going to do this command line. And we'll go back to some of the other scripts. So this is now my command line. I'm going to cut and paste from here and show you essentially the same thing onto the command line now. Oops. So here's the command line. We'll issue some of these commands in there. Okay. Now we've defined it, so we're ready to go. The command line is at the same place where we left off here. Okay. Okay, so let's go back to the histogram. See if we can do this here. Okay, there is a error here, which I guess I didn't catch when I created it. This is a bit weird. Let's go back to the original. Okay, so obviously I didn't put that in correctly. Let's not worry about it. Let's do the color magnitude diagram. Again, very basic. We don't even know what to call them. And what you get out of that, by default, this one shows blue colors for the dots. That's fine. There's x-axis that goes from -6 to 3. There's y-axis that goes from 0 to 16. So this is, first of all, a color magnitude. So we know that magnitude, the brighter ones, are going to be lower values. So the first thing we want to do is flip the axes, so the brighter stars do end up at the top. The other thing is that there's appears to be a couple of stragglers, and for now we don't necessarily want to see them. We want to see what the main group of stars is doing here. So I'm going to do slightly fancier plotting here. So again, issue the figure command. Okay, let's bring it up and then we'll go through it little by little. So now what I've done is in the figure command, again did the scatter, but we added a couple of additional arguments to the scatter. Okay, I wanted to keep the color black, so I introduced that, but then I also changed the transparency by using something called alpha. And that makes it easier to identify where the number of points get very thick. So transparency basically means you can see through the data points. And so if you've got 12 data points that are stacked on top of each other, their transparencies would add up. And you can see that the overlapping parts of the points appear darker than a single point by itself, because if it was 100% transparency or alpha equals 1.0, it would be dark. That means it's opaque. But if it's transparent, kind of like a window, then it's slightly gray. And if you stack multiple ones of them, it keeps getting darker and darker and darker gray until it gets to too many stacking points and you get black points. I find this very useful because it lets you figure out at one glance where the most number of your points lie. Obviously, I could have chosen blue or red or green or any number of colors available to me. The other thing I did was to change the limit. Remember, we had a couple of stragglers, so didn't really want to deal with them, so I squeezed the X limits to exclude those stragglers, and I flipped the axis for the Y limit. These are the commands that do that for me, so that now the lower part is at 16 and the upper part is at 3. So now I know that because it's a magnitude, this is brighter stars up here and fainter stars here. And then there's no obvious sequence here because this is just an apparent collection of stars detected by Ys. Okay, and then of course I added a title, an X label, and a Y label. So all of those are fairly basic things that you can do. Now, the last thing that I want to show you before we get to some of these additional links at the bottom is the use of subsets. Okay, so let's issue this, and then I'll walk you through what each one of these commands does. Okay, so we issue these commands and out pops another figure. So let's see what this figure, how do we achieve this figure? So before we even got to the figure, notice that there is some Python manipulations that we're doing. We're defining a variable called w1 minus 2, which is simply the difference that we had initially put into our scatter plot diagram. But this case, I actually compute it and store it in here. And then because I want to define two different groups, the first group has my w1 minus 2 less than 1. My second group has w1 minus w2 greater than or equal to 1. So I have a blue group and a red group. Okay. Now, once I've made that distinction based on my color, okay, I can then manipulate the figures to show me these different groups. So again, we start with pl.figure to initiate the new figure. Then we add in this command here, scatter. But what's different about the scatter now is following. Okay, I'm going to plot RA and declination. So we'll see if the blue or the red groups occupy different parts of Orion. This looks similar to what we have done, except that after my RA, in parentheses, I've specified group 1. Okay, so that means that the entire vector of RA values only take the ones that are part of group 1. And group 1 was obtained by issuing the numpy where command. Okay, maybe it makes sense to talk about it a little bit. The where command is extremely useful. What it does is it allows you to search and combine searches on vectors. Okay, group 1, when it comes back, let's actually issue this command so we can talk about it. Okay, so we've issued these commands. Let's see what group 1 looks like. There is a buffer. So this is actually the output of group 1. It's an array that has all of these numbers. In fact, each one of these numbers corresponds to the index where this particular condition was true. So group 1 contains all of the access points to the W1 minus W2 vector, where W1 minus W2 is less than 1.0. And group 2 has the same indices. And once you put these indices in a square parentheses next to the vector, then Python knows that only take those values. So here I'm plotting all RA and DEC values with the color blue, where the W1 minus W2 was less than 1. So it had blue colors. I repeat that with color red for where the W1 minus W2 is greater than 1. I supply a couple of labels. You could call it anything you want. You could call it, blue dwarfs or my favorite red stars. But this is just a label at this point. Okay, so then I supply it my X and Y label. Then here's a new command. I actually want Python or this plotting to show me as a legend, as a inset square box, what the different colors or symbols that I've chosen mean. Okay, and then finally the show command. And what we get out of all of that is the following. Okay, right ascension, declination. Okay, we've issued two different scatter plots commands. The first one in blue pointed what I call the blue stars, and then the second one in red plotted the red stars. And I could have put in alpha or any other optional arguments here. I could have changed the symbol from the default to something more fancy. And then I've given each one of those commands a certain label so that when I ask for a legend, that legend appears in the upper left part of the diagram. Okay, I could have said bottom left and maybe have had more room than the upper left. But then it tells me what the red and the blue actually mean. Okay, so quite useful, quite nice. You can play with it. You can create many different subsets. Okay, so this is sort of the very basic in programming that you can do with Python. There's a ton more. And I'm going to bring up a couple of websites that we're going to go over. Any questions at this point?
Actually, not yet, Babar. Thank you. I would like to try to do it.
Yeah, that's the best way to learn, is to actually do it. So matplotlib, which is what we've been using, even though it doesn't sound like it. The web page for that is right here. So let's go to that. There is a ton of documentation and there's a ton of examples. In fact, there's far more examples than you want to deal with. So you really kind of temper your way in to MATLAB. But this is where you would find the help. Okay, examples. You can jump right into it. Yes, you can do animations, animated GIFs. Even I would start with something maybe a little bit easier than that. Okay, showcase, example, XKCD. I'm not even sure what they are, but you can find it here. The other thing you can find is a list of plotting commands. Okay, let's. You can go through this. I showed you. Let's see. Plot, so it's right here, and scatter, which is alphabetically speaking somewhere here, like here. But you can see there's a long list of them. Okay. Each one of them, if you were to hit it, here's histogram that didn't work for us, will take you to the API, which is very useful. Now you can see, bins, range, anything you wanted here. Same with some of these other parameters. Not all of these are plotting. Pie chart obviously will get you a pie plot. Some of these allow you to control the look and feel of the plot. For example, minor ticks off simply means that you can remove. Don't tell Python not to put in minor tick marks, okay, or major tick marks. If okay, I have some gremlins in the system, but let's try it this way. So this here, for example, I only have major tick marks anyway, but you can change that. You can also change. In fact, there's so much that you can change that it becomes almost ridiculous. But getting better at plotting means you basically have to do it and then start learning what some of these commands are. I haven't found an easier or a different way into it. Okay. So gallery is another one, which is a bit more useful in the sense that you can look at a plot and say, well, okay, I'm trying to go for something like that. How did they do it? So polar and pie chart, for example, well, here's one way that you could do it. And you have then the code below it, which you should be able to figure out, how that works by now. And histogram, here we go. There's our failed attempt at the histogram, but there's one that will work if you wanted to try it. We haven't touched a lot of items. For example, you can have two plots side by side with or without sharing the axes. 4 plots, that looks a little overwhelming. But that's your foray into it. If you want to step through this gingerly, the first link is actually another tutorial, which is prepared by somebody else. I actually found this one quite useful when I started. So if you wanted to try it out, again, they're going to go through this. Only thing you have to worry about here is that they import everything. So I'm used to importing it into PL. They import all of the commands and then start using it willy-nilly. Then they can run you through some of these. So here's plot, line width, line style. So again, you're controlling how these graphs looks. And trust me, the amount of flexibility you have is almost overwhelming. Okay. Now they're adding a legend in the upper left-hand corner. Going into some text and also fancier text. For example, if you wanted to put in Greek symbols, you can. It's actually not that difficult. You just have to learn how to specify Greek symbols. How to specify subplots, so you can put multiple ones, and then all sorts of other types of plots that you can do in Python. Okay. Here's another multicolored one. Okay, this tutorial, that's all it is. You just go through it, and it's one example after another, one example after another. Text tutorial even. Okay, this is also, by the way, available from MATLAB. This is the beginner tutorial link that I just showed you. There's more. You can spend as much time as you want, and apparently even NumPy and Matplotlib on YouTube.
So what we're going to be going over today is really...
Okay, the hour is almost up. That's essentially the last topic that I meant to cover. So if you took stock now on the 5 tutorials, you should have gone from not knowing any programming to where you should be able to read some basic data files and manipulate them and make your own color magnitude, or any different types of plots that you like. The best way forward, the best way to learn any of this is to simply keep trying and finding help. You're welcome to send me emails. This will be the last one, so there won't be any further ones out, but I'm more than happy to help when you have time or if you're stuck in a particular problem. Okay. So I will stop here.